Hey kids, so today we're going to learn about shape of molecules, also known as molecular geometry. So you're probably asking yourself questions like, what is molecular geometry? What is the purpose of molecular geometry? Why do we need to learn molecular geometry? How do we determine molecular geometry? How do I pass Gen Chem? Essentially, molecular geometry is the three-dimensional arrangement of the atoms that make up a molecule. In learning molecules, it is important to understand the way it is arranged in three-dimensional space, since it will affect how the molecule does chemistry. That meaning it can determine several factors like reactivity, polarity, color, and even biological activity. Now, how do we determine molecular geometry in a given molecule? An important theory is used to explain and predict the shape of molecules and ions is the VSEPR theory, or the valence shell electron pair repulsion theory. Atoms are surrounded by negatively charged electrons, and when you have atoms in a molecule together, these electron clouds repel each other. It's the idea that the pairs of electrons in the valence or outer shell of the central atom repel each other. So what I mean to say is, atoms also want personal space from each other, just like people in an elevator. So because of this, the atoms form a geometry that minimizes the electron pair repulsion. The geometry around the central atom depends on the effective number of the electron pairs. Double bonds count as one pair because both pairs in double bond are constrained to a point in the same direction. For clarity, the term electron domain will be referring to the lone pair or a bond, regardless of whether the bond is single, double, or triple. By the way, in getting the molecular geometry, you need to identify and add up the valence electrons of the given element, and to do so, use the periodic table of elements and ignore the metals, which is this section right here. And once you've done that, we can see that all the first column equals to 1 valence electrons. So hydrogen has 1. If you have beryllium, you're gonna have 2. Boron has 3, and it goes on until you hit helium, which contains 8 valence electrons. But I mean, sure, you already know that, since I'm sure you've encountered loose dot structures or something. Say carbon dioxide. Carbon lies in the 4th segment of the element. Carbon lies in the 6th. So add those numbers together and we have 4 plus 12, since the molecule contains 2 carbon, and we have 18 valence electrons. By the way, you're going to use the valence electrons because you are going to create or construct a Lewis dot structure in order for you to know the molecular geometry. I kinda forgot to tell you about that part. My bad. Before continuing on, I'm going to inform you that I'll be discussing the 5 basic geometries, which in this case are the linear, tetrahedral, trigonal pyramidal, trigonal bipyramid, octahedral, and also molecular geometries with lone pairs. So let's take CO2 for example. A carbon atom has 2 electron domains of electron density extending from it. In order to participate in these bonds, the carbon takes an s orbital and a p orbital and hybridizes them, forming an sp hybridized molecular orbital. You can count on the electron domain and use that many atomic orbitals to describe the hybridization of the central atom in a molecule. For each energy level, there is 1s, 3p's, and 5d's. So in our example, we can just use 1s and 1p for these electron domains. Everything that is sp hybridized is going to show a linear electron domain geometry, because as the furthest away these atoms can get from each other while being inbound to carbon is this shape, which shows 180 bond degrees. So now let's take SO3 for an example. Sulfur trioxide contains 3 valence electrons, hence it can make 3 bonds. So it means that there are 3 electron domains surrounding the sulfur atom, which makes the sulfur sp2 hybridized. All molecules with sp2 hybridized will be trigonal planar electron domain geometry. It's the furthest that the 3 oxygen atoms can be from each other while still being connected to the sulfur. 120 bond degree is the angle for trigonal planar. Once the central atom contains 4 electron domains, we will start utilizing the 3rd dimension. The chlorine from carbon tetrachloride is sp3 hybridized, so it has a tetrahedral electron domain geometry, and it has a 109.5 degree angle because it is the angle where chlorine can be as distant from each other while still being inbound with carbon. It has a shape with 4 sides if we connect the 4 points, which kinda looks like a pyramid. Now atoms with 5 electrons are s3d hybridized, and the domains will have a trigonal bipyramidal electron domain geometry. The bi from the trigonal bipyramidal means 2 pyramids connected at the same base. So these things actually contain 120 and 90 degree bond angles. An example for this is going to be phosphorus pentachloride. Notice that chlorine has a 90 degree angle from the other chlorine in the z-axis, and it also has 120 in the x and y axis. Atoms with 6 electron domains are sp3d2 hybridized and will have an octahedral geometry resembling an 8-sided figure. All the bond angles are 90 degrees, like sulfur hexafluoride. So in order to figure out the electron domain geometry of a molecule, just wanna count the electron domains, and the number will point out the hybridization, therefore its geometry. Besides covalent bonds and other atoms, lone pairs also count as electron domains. In many molecules, the geometry is often distorted. This is because the electron pairs aren't the same, and the amount of space taken up by bonding pairs may be affected by the bond polarity, which explains why polar molecules like water are not linear like some nonpolar molecules such as CO2 or carbon dioxide. As you can see, molecules such as CO2 and H2O have different shapes from each other even though they have the same amount of atoms. The lone pairs of oxygen are pushing away the hydrogen atoms, which makes it a tetrahedral electron domain geometry with a bent or angular domain geometry, because the lone pairs don't take up much space to the other atoms, while in CO2 doesn't really contain lone pairs, just bonds to oxygen. To summarize, the number of electron domains, whether if it is covalent bond or a lone pair, determines the hybridization of the central atoms. The hybridization should contain as many letters as there are electron domains. The hybridization correlates the molecular domain geometry, and within each electron domain geometry there can be multiple molecular geometry as we replace bonds with lone pairs. When asked to assign these geometries, always start by drawing the correct Lewis dot structure and then just count down the electron domains.